synthesis component. So, but if there's anything I want you to get out of this talk, it's basically that thinking geometrically about things sometimes can be useful. Okay, so what's the basic setup? Well, we're synthesizing terms in Haskell in sort of an editor context. So you're sort of editing, and then you say, okay, you sort of say, give me a type, and I want a whole bunch of terms of that type, sort of generated over the things which are in scope according to this very simple grammar here. And if you think about it for a minute, you can realize that these terms generated by this grammar all have types of the form for all A, F, A to G, A, where F and G are functors, or perhaps composites of functors. And, well, okay, not everything looks like this, right? Sometimes we want to have types that don't have any A's in them. So you sort of add to this setup, sort of pretend, well, sort of model closed types, let's say, as constant functors. Okay? So type constructors which sort of depend trivially on their argument. And the search strategy itself is not so interesting. It's basically just forward kind of deductive search inspired by a kind of analogy between terms of this type and kind of string rewriting. And so in particular, I mean, I'll just mention briefly. If you've got a term of type, you know, for all A, bunch of FIs composed apply to A, to a bunch of GIs composed apply to A, the terms of that type are that look like that anyway, are basically sequences of rewrites with sort of basic rewrite rules. Okay, anyway. Okay, so there's a problem which crops up in this approach, which is basically there's tons of redundancy. There's sort of tons of syntactically distinct terms which have the same semantics. So for example, if you do a search for query for this type, you get a whole bunch of terms which differ in sort of meaningless ways. I mean, they're just duplicates. And these are all semantically identical. So the question arises, from whence cometh the redundancy? And there's sort of a few answers to that. One of them is naturality equations. The asterisk there is because this isn't true. I mean, in Haskell. But only technically, right? And there was that paper. Okay, so for example, if you're not familiar with this kind of thing, you have equations like, okay, safe head will be the thing that list of A to maybe A, which gives the head just the head of the list if the list is not empty and nothing otherwise. So if you take the safe head and then maybe map show onto that, it's the same as if you map show over the list and then take the head. Okay. So in general, these equations kind of look like this. So what they sort of express is when there's some sort of kind of irrelevant ordering that's unfortunately in the term, and you want to sort of quotient that away. Okay, so you can permute these things past each other. The order doesn't really matter. And then the other thing is that there's sort of these pointless bits. Okay, so if you've got length composed map even, well, I mean obviously that's just length, right? Why did you map anything over the list? There was just no point. And in general, this is kind of, well, we'll see what this is. All right. So, okay. So our goal: find a normal form for terms up to some set of equations that we have in mind, like on the last slide, for the purpose of eliminating duplicates from synthesis results. Because if we can have a normal form, we just compare things based on their normal form, and then we can get rid of duplicates. Yeah. All right. So. Okay, so for naturality, there's some thingies called string diagrams, and they're basically drawings of graphs. And essentially, they give us a representation which quotients away naturality and some other kind of trivial equations that I just won't even mention, too trivial to mention. And so you can see, naturality, as I sort of mentioned before, is sort of about irrelevant orderings between subterms. And this graphical notation, I mean, that kind of ordering disappears rather, because. Well, basically because things which have no kind of ordering relation to each other can sort of be pushed past each other. So these two terms here, I can just sort of pull down that second, that red vertex rather, and push up that blue one, and that's sort of a proof that those two terms are equal. Yeah, all right. So and you can see that corresponds to permuting those two subterms there. So I'm not going to explain what string diagrams are. There's no time, but I will just say. Edges are labeled by functors. Vertices correspond to sort of terms in our base set of terms over which we're generating. All right, so that's naturality, and that's how we sort of take care of that. And then we ask, from whence cometh these pointless bits, or these extraneous components, or these Yeah, anyway, I was being redundant. So, all right, so let's look at this kind of example again, right? So we've got length, compose, map, even is just the same as length. All right, so what you do when you want to understand something, you write down an example and you analyze the example, and then maybe you can deduce a general principle. Okay, so we write the string diagram for length, compose, map, even. Trust me, it looks like this. You see I've got these edges sort of labeled by constant functors there, and, okay, that kind of says it goes from list of int to, list of constant at int composed with constant at bool, which is just constant of int. So sort of list of int to int, okay. And, by naturality, we can sort of push up that vertex and pull down even. And we sort of get this picture. And then we ask ourselves kind of what's going on. And we take this picture on the right and we rewrite it as a term, which we know will be semantically identical to length, compose, map, even. And it's fmap at constant functor to int compose length, even, rather. Okay, fmap for constant functors, that just sends everything to id. It just trivializes everything. So we know that term, represented by that string diagram, is just id compose length. Okay, that's just length, evidently, right? So what this kind of picture tells us is to get normal forms up to fmap for constant functors on top of what we have, we should check what's to the right of what. So if we know something is to the right of an edge labeled by a constant functor, we can just cross it out. I mean, it just doesn't matter. And this is something I think, sort of points out kind of the niceness of the kind of geometric viewpoint. This is something that at least to me, is completely unclear algebraically looking at, fmap for constant functors and naturality. Okay, so, right. All right, well, there's no time to talk about the algorithm, but it's rather nice, I promise you. And this is the algorithm for deciding sort of what's to the right of what. And I think, to me, the nicest thing about this algorithm, I'm just trying to give an impressionistic sketch of this work, is it's sort of inspired by this kind of classical, let me not say classical, let me say constructive, type theoretic principle of sort of building up evidence, right? If you want to make a claim about something, for example, like this edge is to the left of this vertex, you need to have some kind of thing which witnesses it, some kind of piece of data which witnesses it. So we ask ourselves kind of what's the piece of data which witnesses it. In this example, I won't get into it. Maybe you can guess by looking at this tantalizing picture. And then later we consume the evidence kind of in the proof of correctness of this algorithm. But this kind of point of view, what's really necessary in developing the algorithm and the proof. Okay, so takeaway. There's an algorithm for putting terms in normal form up to naturality, and fmap for constant functors and other trivialities, which again I refuse to mention. And we apply it to eliminating duplicates from search results in synthesis for this user-facing tool in the editor. And yeah, topological models can help you think. So.
So the sort of graphical idea, is that just for intuition, or does it buy you something algorithmically?
No, yeah, it's not. It's actually like totally essential. It's not for intuition at all. It's also for intuition. Sorry, it's also for intuition. It's not that it's not for intuition at all. But yeah, I literally store the terms. I convert the terms to a graph data structure, and then to find out what's to the right of what, you have to do some kind of algorithm on this graph data structure. And to eliminate duplicates, I just hash these graphs basically.
And you think that's easier than doing some sort of term rewriting?
Sorry?
You think that's easier than doing some more conventional term rewriting?
Well, it was for me. I mean, I guess I guess I'm not so good. Yeah, I mean, I looked at it and I was sort of like, well, okay, I'm not really sure what the normal form should be here. I mean, maybe you can. I mean, there are things you could do, but for me, this was easier to think about. I don't know.
Very nice. So in some situations, naturality transformations correspond to sort of loop optimizations because when you move things over, you're like moving things in and out. Have you considered trying to use this algorithm in those settings?
Yeah, so I think that's kind of a nice point. And when I sort of convert back from graphs to terms, I make some efforts to sort of fuse fmap passes, but I mean, I don't think I make very good efforts, so I haven't really explored that very much.
Well, there's also a case where the normal form may not be the most efficient version because you may want to, keep something somewhere so that, locality is better or something. Well, it's something to think about, I guess.
Okay, all right. We can talk about it later.
So for your example with the pointless bits, length dot map even.
Oh, the extraneous components.
So something I didn't quite understand was, say it was
Where was it?
length dot map negate, for example. In that case, as you say, the dot map whatever is unnecessary because length is just summing up the length of the list. But what if it was, for example, some dot map negate? Are you inspecting the definition of length or something to determine that it actually doesn't matter? How do you do that?
Okay. So some dot map negate. We can draw the picture later, and it's a different situation, I guess.
Okay, so you're like going into the definition.
No.
Really?
It's about the types, actually. I mean, it's about what's parametric and what's not.
Okay. Okay. I think I understand what you're saying. Parametricity. Okay.
Okay. Right. So one of them sort of only requires, anyway, one of them only has a list edge coming into it, and the other one has got a list and an int edge coming into it, or whatever. So.
All right.
I'm wondering if instead of using these as filters after you've generated terms, have you thought about using these diagrams to generate and guiding the search?
Yeah. So I did try that, and I was hopeful that it would sort of speed things up a lot. I mean, because you'd think, well, okay, in my intermediate set of terms, I've got far fewer, right? But unfortunately, it didn't. I mean, the overhead of keeping graphs around was sort of, I think, probably what did it in. But I will say that actually the graphs are also useful for sort of the heuristic I use for ranking sort of generated terms. I mean, I count connected components as part of the kind of quality heuristic, but anyway.
I was wondering, have you compared this with any existing sort of graph rewriting systems or other similar systems? Is this novel?
Sorry?
Do you know that this is novel?
I'm quite sure. So okay. So string diagrams are not novel. I mean, this is a very old idea, right? As far as I know, using sort of this kind of constant functor thing is novel. I mean, I didn't come across something like this. So if you have something else, I mean, go ahead.
No, I'm not an expert in it.
Okay. All right.
I have the feeling that there must be lots of similar related.
I mean, yeah. I mean, this kind of idea is representing things as graphs. It's quite common. So I mean, it's quite possible. I don't know.
My understanding of string diagrams is that they result from a duality operation.
Yes.
And the algorithm that you shows looks like it's doing the same way in the other direction.
Yeah. Basically, yeah.
So does that mean that you could have worked at on the dual representation all the time?
I mean, yes. So somehow, as actual data structures, if you think about the dual representation and you think about this one, they're really more or less the same. I mean, some things are more convenient in one representation to the other, and it can be actually. I mean, the bad thing about the dual representation is that you have to represent identities explicitly. So that makes some things more difficult, and yeah. Anyway.
So your work relies on the strength of both representations. That's what you need to.
Yeah. So I mean, this constant functors bit is basically relying on some kind of useful property of the dual representation.